let's try to solve this problem by using proof by contradiction. So the problem over here is I've got if A and B belongs in the space of integers, and I'm going to claim that A is some number, some integer that happens to be greater or equal to 2, then A does not divide into B. So this just tells you that A does not divide into B, or A does not divide into B plus 1. Okay, so let's kind of rewrite this. Let's rewrite this as follows. Um, let's say I have some statement P that happens to be logically equivalent to this argument of fq then r. Okay, and q in this case happens to be this piece over here. So just so that I use my colors here, let's do this way. Let's use yellow for q, and let's use a conditional statement in blue, and let's use R for green, and everything over here, everything in blue here is basically my Q. Oh, it should be yellow. So everything in yellow is my Q. Okay, so everything over here is the statement Q, and R is everything in green, my conclusion. So this is my R over here, which is this piece here. And P over here is basically the entire statement. The entire statement in orange is basically P, which has been subdivided into these two different components of Q and R. Okay, now what I'm going to do is, because I'm using proof by contradiction, I'm going to assume that the negation of P, which is not P, is actually true. So again, let me be consistent with my colors. So let's assume let's assume that not P is true. Okay, so if I make the assumption not P is actually true, the the intuition here is that by making this assumption, I'm then going to apply some rules of inferencing. And as I apply rules of inferencing, let's say I hit some assertion that, look, after applying rules of inferencing, I'm going to conclude that C is true. But then if I keep on applying this and more rules of inferencing, then I might conclude that not C is true as well. And because of this contradiction that may arise, I'm going to then say that the original assumption of not P actually being true was incorrect. Not P must be false, which implies P must be true. And again, the intuition was provided in my first two videos that I highly encourage watching before jumping to these problems here. Okay, so with this assumption that not P is actually true, what it tells you is so not P is true, which implies that the negation of Q, if Q then R must be true as well, which is the same thing as saying not Q and not R. Okay, so if you're assuming that not P is true, if you're assuming that this is true, well, because I have a conjunction here, it means well, first thing, this entire thing must be true as well, which also means that Q in this case must be true, and not R must also be true because of the conjunction here. So what I'm asserting right now is that Q is true, meaning I'm going to assume that A and B belongs in space of integers, and A happens to be greater or equal to 2. And I'm going to assume not R is true. Well, if R is in this case this entire piece in the green box, then not R is telling you that A does divide into B. Become going to the negation of this. This entire piece over here is R. Not R is the negation of which is A divides into B, and A divides into B plus 1. Okay, so if not R is true as well, and if A divides into B, that tells you that B over A should equal to some integer C, where C is some integer. And because it divides, there's no remainder over here, there's just a quotient, and C happens to be an integer. And likewise, if A divides into B plus 1, that also tells you that B over B plus 1 over A maybe gives you some other quotient D, where D is some integer. Okay, so given this here, given these two here. Now what I can do is I can rewrite this, at least rewrite the green piece over here as saying B, so let's do this way. B equals to CA, and then this piece over here in yellow can be written as B plus 1 equals to BA, which is B equals to BA minus 1, and then just putting the same, but both of these equal to each other. That means CA equals to BA minus 1, and then finally I can say CA minus BA equals to minus 1. Okay, so which is this piece over here, and then finally making A the subject, I can get A of T minus C equals to 1. Okay, now what I know from here is that D is some integer. D is some integer. And I also know that C over here is some integer. So D minus C is also going to be some kind of an integer, but more importantly, it's an integer that happens to be positive. It's going to be greater than 0. Okay, so it's a positive integer. Okay, and because it's a positive integer, because D is greater than 0, I can then say A from this piece, A equals to 1 over D minus C. Now when I say A equals to 1 over D minus C, because I know this is a number that happens to be greater than 0, D minus C is going to be a number greater than 0, and because it's a number greater than 0, then this entire piece over here will never ever be greater or equal to 2, because my assumption originally was not P is actually true, which meant that Q in this case is going to be true, and Q was this entire statement in yellow that I'm claiming that A must be greater or equal to 2. And I just concluded that A cannot be that. A must be a number that happens to be less than 2. Okay, in fact, definitely going to be, in this case, less than 1. So because of this contradiction, I know that my assumption of not P actually being true is false. This is false, meaning not P is going to be equal to 0, 0 indicating false, which means that P, the original statement P must be true. And the original P is this entire box here in purple. Okay.